Hi everyone, welcome to the this year's session of the Random Geometry and Statistical Physics seminar. Today's talk will be by Lukas Schoug from the University of Cambridge. We'll talk about the regularity of SLE4 and SLE8.
Yeah, thank you for having me. This is So I'm going to talk about the regularity of the SLE4 and the SLE8, and this is a project which is joint with Jason Miller and Konstantinos Kavadias. So I will keep it, somewhat intuitive heavy more because I don't feel like going into the details of, of the quantum surfaces because that would not be enjoyed by too many of you. So I'll first briefly introduce the SLE, which I'm sure that you all know. And then I'll go on with the main results and then discuss briefly the ideas for the proofs. So first, SLE is a probability measure on random fractal planar curves, and they arise as scaling limits in two-dimensional statistical mechanics when you consider the models at criticality. They are conformally invariant, meaning that if you define these curves in two different domains, then the laws of the law of one is just given as the pre-image of the former. These are parameterized by one parameter, kappa, and it gives three phases. So, for example, for kappa between 0 and 4, we have simple curves. We have self-intersecting curves if kappa is between 4 and 8, and we have space-filling curves if kappa is greater than 8. So we can basically see here in the simulations by Tom Kennedy that for kappa is equal to 2, it's this fractal object, which is not that rough, whereas when we increase kappa to 3, then it's more rough. You see that it almost intersects itself. And whereas for kappa equals to 6, it does intersect itself, and it's way more rough than previously. And then if you were to consider kappa greater than 8, then it would just grow as a blob. So the way that we go about and define them is that we consider the Liouville differential equation, which is given here. And then we just plug in the function ut given by square root of kappa times the Brownian motion. And when doing so, we solve the differential equation and we get a family of conformal maps such that so now considering kappa less than 4, just for simplicity, we get that they take the exterior of the curve back to the upper half plane. So this generates a family of curves whose domain is given by the exterior of some curve, and this curve is what we define to be an SLE. SLE kappa for kappa between 0 and 4. And in case you have kappa between 4 and 8, then you just take the unbounded connected component of this curve will be the domain for the map GT. These curves have been heavily studied in the last 20-25 years, and for good reason. They exhibit very interesting geometry. And so here is something called a chordal SLE, which is what you define in a simply connected domain between two boundary points. And to get it in any other domain, you just take it by a conformal map from the upper half plane version that we have here. So as mentioned here, in any other simply connected domain, it's just the conformal image. Then there exists also radial and whole plane versions. The radial version is a curve growing from the boundary to the interior to some fixed target point. And in the whole plane case, you get a curve growing from 0 to infinity. And locally, these curves look just like the chordal SLE. So there are many previous results, of course, relating to SLE, but the two results that I would like to bring up here are the ones which are most related to the results that we have in our paper. So, okay, so I have not yet defined the uniformizing map, but it will come in a few slides. So if you take an SLE curve in the unit disk, for example, from -I to I, and you define the uniformizing map, then you can see that it's Hölder continuous, and the optimal exponent was determined by Ewan, Jason, and Shin. And in the case of SLE kappa, where kappa is not equal to 8, then you know that the curve itself is almost surely locally Hölder continuous, and the optimal Hölder exponent was determined by Frederick and Greg. So these two are the results that we kind of where we want to fill in the gap in this project. So as you can see here, I mean, we have the problem where kappa is equal to 4 and where kappa is equal to 8. And the reason for this is that, I mean, you see here that this a slightly poor drawing of an SLE4 and a slightly poor drawing of an SLE8. But the point stands here that wherever at whatever scale you look, these curves will almost intersect itself. It's just, I mean, SLE4 is just at the boundary of the non-self-intersecting regime. So if you just were to increase kappa by the slightest amount, then you would immediately have a self-intersecting curve. So this means here that in the SLE4 case, this curve almost intersects itself. So it's, I mean, it gets infinitely close to its past all the time, basically. And this causes a problem when analyzing it, because something which is nice here, you can see in when you look at, for example, the Hölder continuity here of SLE, is that whenever you take a small ball which is close to the SLE, I mean, you take a small ball centered at any point in the SLE, then the harmonic measure of that will decay as a power of epsilon. However, in the case of SLE4, this is not the case. So then it could decay. The harmonic measure could decay way faster when sending epsilon to 0. And the same thing holds for SLE8, but instead we have to consider the tip here. So the SLE8 is this case here with the Hölder continuity. Because then if you look at the outer boundary here of the SLE8, then these two are given by SLE2 curves. And if you know your imaginary geometry and you send out to these two interior flow lines, you know that the rho values for these will be just so that these two curves do not intersect. But just in the case of SLE4, they get infinitely close to intersecting. So in the same way as for the SLE4 here, a small ball centered at the tip, I mean, the harmonic measure will decay super quickly quite often. So yeah, so this is the reason why SLE4 and SLE8 are troublesome. So just before moving on to our first main result, we define the uniformizing map of SLE4. So if you pick an SLE from SLE4 from -I to I in the unit disk, and you define the DL to be the part of the disk which is to the left of the curve, and then you just pick a conformal map from the unit disk to that set DL, fixing I, -I, and any other point. Let's just say that we fix -1 as well. Then this is the uniformizing map. So the first result is that, I mean, if you just ignore all of the text here, this is just defining the uniformizing map. then we know that the uniformizing map has this modulus of continuity. So, and this is in fact, basically the best we can get, because if we were to pick any zeta less than 0 here, then we would be in this regime, and here we know that this is almost surely infinite. So if we were to pick any zeta less than 0, then this would almost surely not hold. Almost surely this will not hold for all Z and W outside of these small balls centered at -I and I. So this is basically the best kind of regularity that we could hope for. We don't know exactly what happens if we were to pick zeta is equal to 0. It could, so we're not sure if we would need some log correction or something here at best. But yeah, this is close to optimal. And this, you will see later that this result is basically the same result as in the case of SLE 8, where we take the modulus of continuity for the trace of the curve, which was, and the result for the SLE 8 was predicted by Greg Lawler and Liouville, I think. But I will get to that result. So before moving on to SLE 8, we take a quick detour because the next result is also an SLE 4, and it concerns the conformal removability. And before anybody gets too excited, no, we have not proven that anything is conformally removable or that it is definitely not conformally removable. That would be very nice, but we haven't done that. But so first, we define a set K in the complex plane to be conformally removable if every function phi between the complex plane itself, which is conformal outside of K, is also conformal on K. So in a sense, this says that the set is not too big because it cannot influence the conformal map too much. And so if we pick two copies of the unit disk, D1 and D2, and we have a homeomorphism between their boundaries, then a conformal welding with a welding homeomorphism phi, defined there, consists of a closed curve on the sphere and a pair of conformal maps taking each of these unit disks to the two different sides of the sphere when it's cut by the closed curve. So at first one can ask oneself, why is this conformal removability something that you should care about? Well, if you do this welding homeomorphism and everything, it's a priori not clear that the curve should be unique or anything. However, if you have this conformal removability of the curve, then you know that it is the only curve that could arise from a welding homeomorphism as that. Which is very nice considering that there's a lot of conformal welding going on in our field. So, for example, if you were to weld together something known as quantum surfaces, that's a very powerful technique that we can use, and then it's very important to know, for example, if the curve is conformally removable, and whatever curves we get when we weld two quantum surfaces in a clever way is an SLE type curve, and we know for SLE kappa less than 4 that this is conformally removable. And so one of the most common ways to prove anything related to conformal removability is to try and check the conditions which were outlined by Jones and Smirnov. So they state several sufficient conditions for a set to be conformal removable. And these have kind of been the way to fix things. So for example, the first one is that the set K is the boundary of a Hölder domain. And this is, I mean, this was proven, as I mentioned before, for the regularity of the SLE. So just knowing that immediately implies then that the SLE kappa is conformally removable for kappa less than 4. So this then, of course, makes sure that these conformal weldings of surfaces are unique in the subcritical case then, that is kappa less than 4. However, there's an open question whether SLE4 is conformally removable or not. And our next result is, I mean, we don't address immediately what it should be, but it just says that it just tells you in what direction to look for tools, or more precisely in what direction not to look for tools. So first, you define this quasi-hyperbolic distance. It's just the distance that you get by when integrating your curve. You weight by the distance by 1 over the distance to the boundary. And then, so we suppose that eta is an SLE in the unit disk from -I to I. And again, we pick dl to be the component to the left. Then we know almost surely that for any fixed zeta 0 in this domain dl, we have that the distance, the quasi-hyperbolic distance, as seen from the point z0, is always is never an L1 function. And this is problematic or good or whatever, for the reason that all of the results of Jones and Smirnov they depend on an observation that the sum of the shadow of a certain of the set that you're looking at with respect to some family of geodesics should be finite. However, this implies that the quasi-hyperbolic distance, it implies that the sorry, I got a call. And it's supposed to be and this implies then whenever you consider, for example, the quasi-hyperbolic geodesics, it implies that this quasi-hyperbolic distance is an L1 function. So either you would have to consider completely new types of results, completely looking for anything other than the Jones-Smirnov paper, or you would have to pick some clever choice of geodesics. However, these quasi-hyperbolic geodesics are really, I mean, they're really the go-to geodesics to work with there. So I would advise anybody to approaching the question of conformal removability of SLE4 to try to look for different tools, unless they're very very strong with these different kinds of geodesics. And finally, so we have this modulus of continuity result for SLE8. And as I advertised earlier, that you see that this is basically the same modulus of continuity as for the uniformizing map of SLE4. Just replacing this 1 over 3 in the SLE4 case with the 1 over 4 in the SLE8 case. And this was basically predicted without mentioning explicitly what exponents you should have here in a paper by Greg and Alvisio. However, I mean, if you read the paper, you could basically see that they know that this minus 1 over 4 was the right exponent. They were just not they were just not telling anybody explicitly. So yeah, so this so we proved their conjecture, and just as in the case of the uniformizing map for SLE4, we don't know what would happen if we were to pick zeta is equal to 0, for example. If there would be some log correction or whatever. However, we know that, if we were to pick zeta less than 0, then this would not hold almost surely, because of the second part of the theorem. Okay, so let's see how much time. Yes, 20-25 minutes. So just stop me at any moment if you have any questions. Okay, yeah, Greg wrote the names there. Okay, yeah, thank you. Okay, so let's move on to the main observation. So the main idea that we had was basically to use the escape probability of Brownian motion that started very close to the curve. And then we could relate this both to the uniformizing map, to the derivative of the uniformizing map. And then we could also relate it to the quasi-hyperbolic distance between 2 points, with 1 point very close to the boundary, as well as the half-plane capacity of a set very close to the tip for the SLE8. So basically the way to do it is just to check so if you start with a point here, super close to the curve, and you want to know, like the probability of reaching this blue set out here. Taking the pre-image back to the unit disk here, this is by conformal invariance of Brownian motion. The probability of this of Brownian motion started from this point here, reaching the blue line here before hitting the curve, is just the same as the probability of hitting the blue line here before hitting the boundary of the disk. And moreover, the probability of hitting this blue line here is basically the same as the probability of hitting this purple circle here, because we're going to choose the point to be super close to the boundary. So then, traveling half the radius or 3/4 of the radius of the disk doesn't matter. So, and if we have very good estimates. We know precisely what's the probability of hitting this interior circle, for example. And that's a very quick exercise for anybody to do in complex analysis or probability or whatever your flavor of the month is. So then this gives us immediately a good bounce on the derivative, and with these bounds on the derivative, one can then get to the regularity of the uniformizing map. And basically the same thing can be done with the if you were to consider SLE8 and you let the curve grow. You say that you start some point here. The probability of escaping from very close here to the tip and escaping and hitting the real line away from the curve is basically the same as just going up and hitting something here. So when you have done a proper change of coordinates with one of these maps in the Liouville chain, this amounts basically to just a gambler's ruin estimate to see, okay, so how far up did this did a point close to the tip go, and this gives you a nice estimate on the uniformizing map, or on the Liouville chain here. which then gives you good estimates on the half-plane capacity. Okay. So the object then is to estimate the probability that the conditional probability that a Brownian motion started within distance epsilon of the curve is likely or unlikely to escape a macroscopic distance. So that's the kind of estimate that we want to deduce. So I will just briefly, introduce the Gaussian free field and the Liouville quantum gravity, which I'm sure for the most of you is already known at a higher detail than I will tell you. But I mean, this I'm hoping to please the people who are not experts in this field. So just briefly, we pick a domain D, the Jordan domain, and we let this H01 denote the Hilbert space closure of these compactly supported smooth functions on that set under the norm given by this Dirichlet scalar product. Then we pick an orthonormal basis with respect to this Hilbert space, with respect to this scalar product. We pick an IID sequence of normal 0, 1 random variables, and we define a zero boundary Gaussian free field on the domain D as just this sum of the product of alpha n and phi n. And we know that this is not a function, but a random distribution. And then, of course, we're not working with the zero boundary Gaussian free field per se, but but the quantum surfaces will utilize random distributions which locally have behavior looking like the zero boundary GFF. So the quantum gravity surfaces are basically models of random surfaces which come with a measure and a conformal structure. So morally, you can view it as a Riemann surface with metric tensor e to the power of gamma h of z times this dx squared plus dy squared, where h is some random distribution which locally looks like the Gaussian free field. However, I mean, this of course doesn't make sense because I mean this is not a number, this is a distribution, and so of course one cannot just do that. So instead, I mean, one has to define it a little bit differently. So you take it as an equivalence class of pairs dh, where you have a simply connected domain D and a random distribution H, where you define two surfaces to be equivalent if there is a conformal map psi from D tilde to D, such that this distribution H tilde is given by this expression. And I mean, then associated with each surface comes a quantum area or mass measure, mu h dz, which you define like this, where you take, instead of having just the Gaussian free field or whatever random distribution, you pick the average value of the distribution on the circle of a radius epsilon, and then you renormalize by sending epsilon to 0 and multiplying by the power of epsilon, which is gamma squared over 2. And this defines a measure, and moreover, this measure is invariant under this change of coordinates here for the random distribution. So this tells you exactly why we define it as an equivalence class of these pairs. And you can do this for gamma between 0 and 2. However, if you pick the case 2, you would have to have a log correction here as well, because this is the critical case for LQG, so the measure would look slightly different. And you can also define a quantum boundary length measure in a similar way. You just divide by 4 here, and you pick a point on the boundary. And of course, you would have to have a quantum. You would have to have a random distribution, which is not the zero boundary GFF, but for example, a free boundary GFF, or any other nice kind of distribution, which would give you something at the boundary rather than just 0. So any questions so far? Okay. Just stop me at any time. So one of the nice features of these quantum surfaces is that you can cut or weld them together using SLE kappa curves. So for example, if you pick a gamma quantum surface and you pick an independent SLE gamma square type curve, typically an SLE kappa rho, where you choose the weights in a proper way. Then this curve divides this upper half plane into 2 parts, the left and the right. And if you have been somewhat clever when choosing these things, then the resulting quantum surfaces, when you pick the restriction of the distribution to the left and to the right parts, their distributions are known, and they are independent as quantum surfaces. And here, of course, I mean, it's not important that you pick the upper half plane or whatever. You could just pick any domain. I mean, due to this invariance here and the conformal invariance of SLE. And similarly, you can do it for quantum surfaces which are parameterized by the complex plane. However, I mean, it's advisable then to pick a whole plane SLE rather than just some. I mean, you wouldn't be able to just cut it with a chordal, because I mean, where would you start it? And this welding is this kind of cutting and welding result is well understood in the case gamma between 0 and 2, because then that's when you cut with kappa is not equal to 4 type curves. And it's less well understood in the critical case gamma is equal to 2. That is when you pick kappa is equal to 4. And when I say less well understood, you have to take that with a grain of salt, because I mean, people know exactly what happens, I guess. It's just that it's a bit cumbersome and everything hasn't been written down yet. But several proofs of welding these things, welding these critical quantum surfaces, have been appearing in recent years. I guess Nina and Ellen have been responsible for a few results in this direction, and probably more people that I'm not mentioning right now. However, for the particular case of quantum surface, for a particular case of critical quantum surfaces that we need to do it, it was not written down. So we proved a theorem on cutting critical quantum cones into two critical quantum wedges, basically by taking one whole plane SLE, SLE4, and then cut, and then in the new domain we defined chordal SLE4, with proper weights, and we show that the resulting surfaces are quantum wedges with parameter gamma is equal to 2. But I'm not going to talk anything about that. It's just something that I should mention before going into the proof idea. So the way that we try to handle an SLE4 is to approach it via whole plane SLE4. So it turns out it's easier to handle the two-sided whole plane SLE4 than to handle just the SLE4 in the unit disk immediately. And the reason for that is that if you take this two-sided whole plane SLE4 from infinity to 0 to infinity, then, I mean, however you do this, whenever you just shift, you make a shift in time and you recenter the curve, the law of the curve is the very same as the one you started with, which is very beneficial because then you basically just have to consider what happens close to 0, because, I mean, if you just shift any positive time, you're in the same situation again. So we kind of want to, instead of trying to analyze anything happening in the disk, we analyze what happens in the whole plane case. But then we of course have to transfer it to the unit disk. So if you consider the uniformizing map phi taking the unit disk to the left side of the curve, then this is you can get this map by taking a whole plane SLE4 from infinity to infinity through 0, and you consider the map from the unit disk to the left side of that curve, where you define left to be in some canonical way. It's, I mean, if you start with two curves going from 0, then you just pick whatever curve you want to tell you which is the right direction to choose. But I mean, by symmetry, each of the sides will look the same. So you take this conformal map from the unit disk to the left side of this curve, and then you take a new conformal map from the complement of this curve eta 1 to the unit disk, because then this takes everything outside of this blue curve here back to the unit disk. So this boundary here will just be the blue part here, and the resulting curve here is just an SLE4 from 0 to infinity, which is mapped here, so it gets from -I to I. And the reason is that you can, when defining this this whole plane SLE4 from infinity to infinity through 0, you basically just pick one whole plane SLE kappa rho, one SLE4 rho from 0 to infinity, and then given that curve, you define you then sample an SLE4 without any weights from 0 to infinity, and then you get this two-sided whole plane. So this gives us a way then to check what happens here in the whole plane, and to say that, well, this is fine because this will tell us exactly what happens in the unit disk, explicitly, because this conformal map here, I mean, it's smooth on this red curve here. So any possible problems that one could have is just around 0 and around infinity, which is also the reason, if we go back to the theorem here, you see that we take out a small portion of the disk just around the endpoints of the curve, and we say that we have this regularity in any outside of these small disks, and this holds for any xi, so it's not something big, but it's just to ensure that that there is a constant like this. So for any xi, we can get this constant. But if we were not to cut out these disks, then we wouldn't be able to guarantee that there is a constant like that. Okay. And this is fine now, because also we know that we have this kind of welding result for these for this whole plane SLE4. So now we want two types of bounds. So this is what I call, the upper bound, because it amounts to this is what gives us the upper bound in the theorem. And the next one gives the lower bound. So this is basically just text telling us, okay, so how to sample our whole plane SLE, and then the SLE4 after that. And then we just let E be the event that there is some point Z close to the curve, so close to 0 here, but not too close to the curve. So it's within distance 2 epsilon, but at least distance epsilon from the curve. And it needs to be, to have harmonic measure at least 1/4 on each of the sides. So basically this amounts to saying that, well, the point lies somewhere in the middle between these two curves, but not super close to this curve or super close to that curve. So it should be, not equally likely, but somehow the same order of probability of hitting the red one as the blue one. So E here is the event that there is such a point, such that the probability of escaping to the unit disk, so say that you have the unit disk defined here, the probability that the Brownian motion escapes all the way out here, is at most e to the power of minus epsilon to the power of minus sigma. So then we want to say that the probability of this event here is of order epsilon to the power of sigma over 2 plus some small order of 1 as epsilon goes to 0. And of course, I mean, this lemma is not right. This is wrong. Of course, we need some regularity and whatever to actually make sure that things work when we want to do the estimates to get the modulus of continuity. But this is kind of this is the type of estimate that we want, and it's more it's easier to state like this, and I guess I think it's doing you a favor not writing all of the regularity assumptions. And then we have the next lemma, which is basically the same thing. It's just that the probability. So the first lemma says that it's unlikely that this is that we cannot get a better probability than this of escaping. However, the next lemma says that it's, well, I mean, it's not super unlikely in the sense that these two give the same order bounds basically. This says that, well, we're at most this likely to get this kind of behavior, but the next one says that we're actually about that unlikely to get the behavior. So this tells us that we're not super unlikely to be in the situation that the Brownian motion is not able to escape with a higher probability than that. Okay, and again, I mean, there are a lot of regularity which is not included in this statement, and probably I could just slim it down to have a nicer statement than this anyway. But the thing here to consider then is that we also had to stop the curves here, because there's a problem in this direction if we let the curves go away and then considering it coming back. So this is kind of a regularity assumption as well, that it shouldn't come back too close. So there's some regularity assumptions in this, but not close to all of them. So these are the kinds of bounds that we want to prove. And so basically, this is how we go about. We start with we pick a ball close here to 0. Of course we have to prove that we can actually fit a small ball close to 0 here. But I mean, we can do that. So it's hidden, that result is hidden in the appendix, basically. So we want to check that, okay, so if we start a Brownian motion from somewhere in this ball, how likely is it to go away, and how likely is it to not be able to go away? So I mean, the way to do this is via Liouville quantum gravity surfaces. So we just define a quantum cone with some proper parameter values. And we sample 2 independent SLE4 type curves from 0 to get this two-sided whole plane SLE4 type curve. And then this two-sided SLE cuts the quantum cone into 2 quantum wedges, basically by the result that I mentioned briefly before. And then we take a conformal map psi, which takes the left side here of the curve with whichever side you define as the left to the strip, and it sends 0 here to -infinity and infinity to +infinity. So basically, any set which is super close here to 0 should be far to the left in the strip. Then we have, of course, that Brownian motion is conformally invariant. So traveling here from a point in this ball and traveling far away on any of these 2 curves is essentially exactly the same as starting a Brownian motion in the image here of the ball and having it travel far to the right in the strip. So basically to estimate this, we have to check how far to the left does this image, how far to the left is this ball mapped by the map psi. And then morally, we can just think of it as, well, if it's super far to the left, we basically have to just estimate the probability that it gets to the line, which is where the real part is equal to 0. Of course, there is more to it, but this is the basic idea. So we do these moment estimates for LQG surfaces. So we know, for example, that B and W epsilon, and hence its image, does not have too small or too large mass. Basically, we can say that it has at least a power of epsilon mass, and it has at most a smaller power of epsilon mass. And then we look at the quantum wedge. So this is a Q quantum wedge. This means that if you look at the distribution here, which defines which is used to define the measure, is given by, if you take the projection to the function which you have one which is basically just the free boundary GFF part on these vertical lines, and then you have a continuous part which basically tells you how much mass is far to the left and far to the right. So that's basically what's going to be the difference, to tell you the difference between the different regions. So basically, the projection onto these curves here, which have average, which have fixed average here on these vertical lines is given by a Brownian motion started from 0 if you go in the right direction. And it's given by the negative of a three-dimensional Bessel process if you start from 0 and go in the left direction. And as you know, a three-dimensional Bessel process, is it's a transient process, so it will go up to infinity. In this case, minus infinity, because we take the negative. So this tells us that very far to the left, the mass of this set, the mass in this strip is very small. So basically, we can say that everything that is to the left of some line here in the strip has very small mass if you pick the line to be very far to the left. And so if you just pick a line which is sufficiently far to the left, then you know that the everything that's to the left of that will have a mass which could be some larger power of epsilon at most. And you can pick that power to be larger than the power of epsilon mass, which is in this set here, which makes sure that, well, okay, then this set cannot be that far to the left, so it has to be at least a certain way to the right. So this gives us a lower bound on how far to the left this set is. And we know, it also basically gives an upper bound on how far to the right this set can be as well, because I mean it still has very small mass, much smaller mass than it would have if you were to put it, to the right of this real line is equal to 0. This real part is equal to 0 line, but yeah. So this is the way to make sure that it's not too far to the left, but not too far to the right either. And if you know that, well, it's not too far to the left, then you know that, well, the probability of a Brownian motion escaping from this point here in this set and going to this real part is equal to 0 line here, you have very, very good estimates on that. You have up to constant estimates on the probability of doing that. So then you're fine, basically. And then, of course, the other direction of the bound that you want, then you just pick. You need to make sure that this image is not too far to the right. So then you basically have what's the escape probability of Brownian motion started super close to this to the point 0 here if you have this two-sided SLE4 curve. And by translation invariance of this curve, you have it for any point on the curve. And this is the key estimate to the first two theorems. And you can do similar thing with SLE8, because I mean if you grow an SLE8 on top of a quantum wedge, then stopped at any time, the quantum wedge, the restriction of the quantum wedge to the outside of the SLE8 curve is still a quantum wedge. So you can map it to this strip, and you basically have the same estimate one more time. Then, of course, I mean this is not everything that goes on, because I have been lying to you a bit, because it's not sufficient just to say that we have to get to the right side of this real line is equal to real part is equal to 0 line. In reality, we do this estimate that, well, it should travel at least a certain quantum length part of the boundary, so that it should pass the point where the quantum length is at least log epsilon to the power of -1. Because I mean, actually getting these Euclidean distances via quantum surfaces is a very tricky business. But it makes for a nicer story when giving a talk like this. So say then that you have this you have these two lemmas. So then you just have to deduce the result as well. So the first part in the first theorem, you basically just use the non-self-tracing property of SLE together with the upper bound. So basically, the non-self-tracing property of SLE tells you that, I mean, this SLE curve does not, go back and just trace itself, but you can always find super small balls to separate, the curve from its past to some degree. And then within these balls, you can just check that, well, I mean, the escape probability of Brownian motion gives us an estimate on the conformal map, on the derivative of the conformal map, which is the uniformizing map. And when you have this estimate on the boundary, on the derivative of the uniformizing map close to the boundary, then you can extract the the continuity of the uniformizing map at the boundary. And then you just have to you just have to be somewhat clever to note that, okay, so if we have this regularity on the boundary, then we can extend it to the interior of the domain as well. But that doesn't require too much work. And then to get the second part, you do a very classic pocket argument. So basically, you need to make sure that, well, this should happen. So the second half is this. Okay, so the second half is you want this to happen almost surely. So you basically need to prove that, well, with positive probability, it happens somewhere. And if you have that with positive probability, it happens somewhere, and you do these pocket arguments, here. So basically, you send your SLE, you send to SLE type curves. If they intersect before exiting this half annulus, then fine, that's very nice. If it doesn't, then, well, sure, just continue to the next annulus. And then you send these two flow lines again, two level lines, in this case, because SLE, we have SLE4. Then you know that, well, the resulting curve that you have in here, in this pocket, is an SLE4 type curve. So you just map it to the unit disk. Here it looks basically just like the SLE4 curve that we already considered, but we have some weights on the left and the right side. It is actually an SLE4 raw type curve. However, just mapping back a small segment here, make sure that we get make sure that the force points go away from the curve. You can do that in both places here, and so that it actually looks like the original SLE, as long as it doesn't get too close to the boundary. So basically, if you know that this the second part of the theorem holds with positive probability, then you can get it almost surely by just considering making pockets in all of these consecutive annuli. And of course, there is some subtlety to it again that I'm not telling you about, because I mean, just to get the positive probability, we already have to make a pocket argument. So it's basically a double pocket argument. First, you need to make sure that this with positive probability, to get that, you form a lot of pockets, and make sure that you can form sufficiently many pockets and that the probability is sufficiently large, so that with positive probability it should happen in one of them. And then we have positive probability that it happens globally. Then you can just continue to get the almost sure result by doing one further pocket argument, which is the one described here. So yeah, I'm running out of time, which is fitting because this is basically the last slide. So so phase 1 here was basically strategy for proving the estimate. Phase 2, well, who knows? And phase 3 is profit. That's when you put it on archive. And of course, this paper, when we started out and we had the idea for how to prove things, it seemed like phase 2 would be super simple, and we thought that, well, this will be a paper which is roughly 20, at most 25 pages. But it turns out that this part was way nastier than we anticipated. So this happened to expand the paper from 25 pages to 90. But I hope that I have conveyed the main idea behind it, because the main idea is actually very, very simple. So yeah. So thanks for listening.